And welcome again. There is one more simple problem waiting for you. And as you can see at your screen, the statement of the problem is the axes of a solid and thin walled cylinder are connected by a weightless rod. Mind it, it's a weightless rod. And the next line of the statement says the cylinders roll without slipping down the inclined surface of a wedge with an angle at the base of alpha. Okay, base angle is alpha, and it's an inclined plane. The radii of the cylinders are the same and equal to R, capital R. That's right, that's fine. That's one information. While the mass of the solid cylinder, that is the forward one, is M1, and the mass of the thin walled cylinder, that is backward at the greater height than M1, is M2. Find the angle alpha at which the cylinders will roll without slipping. That's the question, rolling without slipping. And then that's simple because yeah, you can see in the picture we selected a lab inertial reference frame, and this is really rigidly attached to the inclined surface that is not moving with respect to ground. That is why it is lab inertial reference frame. And as you can easily recognize the x and y axis, x is along the incline in downward direction down the incline, and y is perpendicular to incline upward, but in the sense vertically upward sense, not direction. And the cylinders in the process of their planar motion are acted upon by the forces. You can easily recognize the forces of gravity, that is M1g, M2g, and the friction forces, that is F1 and F2, acting up the incline. And also the forces of normal reaction, you can recognize N1 and N2. And don't worry about this picture. This was basically become impossible to delete some of the lines, so it looks like that. You don't need to worry, and you can find the direction of N2 acting, and this is normal. And you can also see the reaction forces of the rod. It's weightless rod. I treated it as a weightless string. So you can see here the tension forces that are simply reaction forces of the rod, nothing else. The rod is pulling both the cylinders. So how can it pull the lower cylinder and the upper cylinder? You can easily recognize the things, and don't need to worry about. So let's move to write the equations of motion, system of equations of motion. Of course, I would first like to write the equation of motion of the center of mass of the cylinders along x and y axis. That is why this coordinate system is selected. So I'm going to write its equation along x and y axis. The equations of motion of center of mass of the cylinder, and let's write one. Uh, which one should I write first? I'm going to write the equation of motion of center of mass of this cylinder first, solid cylinder. So I'm going to write down its the component of m1 along the x-axis. So I'm going to write down the component of projection of m1g along the x-axis. That will be m1g sine alpha, and a tension in opposite direction I can see, and the friction in the same direction, so minus f1, and that is going to be the m1. M1 is the mass, I suppose m1 is the mass of the solid cylinder, yes, and its acceleration. This is my equation number 1. Simple. Think first, difficult things come later. And so we can also write the equation of motion of center of mass of this hollow cylinder along the x-axis. I can see here This is the M2G sine alpha, that is the projection of M2G along the x-axis. So I can write here M2G sine alpha, and then tension is acting in this direction, so I'll also give it a plus sign, and friction in opposite direction, that is F2, and that will be the acceleration, mass into acceleration of the hollow cylinder, that is M2. And that's okay, both will have the same acceleration. I don't need to tell you because you can easily recognize this is a weightless rod, rigid rod, so both centers of the both will have the same acceleration along the x-axis, I can say, which is also the center of mass of the system. And since we need to find the angle alpha at which the cylinder will roll without slipping, so I'm going to write down the equations along y-axis as well. So for the first cylinder, this one is nothing but n1 equals m1g sine alpha, m1g cos alpha. So I would like to write as n1 equals m1g cos alpha, and n2 is also equal to m2g cos alpha. m1g cos alpha, n1 is equal to m1g cos alpha, and n2 is equal to m2g cos alpha. And so let's get it done. These are the equations of translation, equations of motion for the center of mass of the cylinders, and we are now going to move the equations of motion for the cylinders relative to the axis of rotation, passing through their center of mass. Why I'm choosing center of mass? Because I don't have a single instantaneous center of rotation. In this case there are more than one body, so I'm going to use their respective center of masses, so that the center of mass is my choice, mainly because I don't want to see this T in action. This T is bothering me, so I'm going to use the center of mass of the cylinders to write down the equations of torques, moments. And for the lower cylinder, it can be simply only one force is producing the torque about the center of the solid cylinder, that is F1, and nothing else. All are passing through its center of mass. So the torque equation simply for the lower cylinder will be F1R, R was its radius, remember, equals its moment of inertia, that will be mr square by 2, I guess. Only mr square. And I1 and its angular acceleration, what should I write? Let's write it beta. So its angular acceleration is beta. Now for this is set of equation 3, and this is equation number 4, and I can do the same with hollow cylinder, and it goes nothing but again F2R is equal to its moment of inertia is different, and its angular acceleration will be also same. Why? Because angular acceleration and acceleration are related in this case, because both are rolling without slipping, are nothing but they are related to A equals beta into R. Since their R's are different, their radii are same, sorry, not different, radii are same, age same, so beta must be same. So beta, the angular acceleration, is same for both cylinders, and I know I1 solid cylinder, its moment of inertia will be half mr square, yeah, and I2 will be m2r square, simply it's like that. And now what? Now we need to find what? I guess we needed to find out n1, n2 is already found, and we need to find two things from these two equations. So you will be going to find it out, F1 and F2. Just find the values of F1 and F2. N1 and N2 you already got, and the statement of the problem that read something like that. Find the angle alpha at which the cylinders will roll without slipping. We are going to solve it. That means we needed to find out the maximum value of static friction acting on them, because after we increase the alpha more than that, the cylinders are going to slip on the inclined plane. So we already know F1 is less than equal to mu N1, mu was same for both, and F2 is less than equal to mu N2. So in the when they are on the verge of slipping, F1 will simply become mu N1 and F2 will become mu N2, as we know from the basics of friction forces, basic nature of friction forces. And we have what N1 equals M1G cos alpha and N2 equals M2G cos alpha, like those. So we can find F1, F2, and I have just found it. Where is it? Yes, I got earlier F1 equals M1 plus M2 divided by 3M1 plus 4M2 multiplied by M1G sin alpha, and F2 I got is 2M1 plus M2 by 3M1 plus 4M2. M2G sin alpha, both are different, you can see here. So after putting them cos alpha, sin alpha, there is F1 equal to mu1, N1 contains cos alpha and F1 contains sin alpha. In both cases, try to find out tan alpha. In both cases, in the first case, the value of tan alpha you are going to get is equal to mu 3M1 plus 4M2 divided by M1 plus M2. And the second case, you are going to get its value equal to mu 3M1 plus 4M2 divided by twice M1 plus M2. So you can see here, the right hand side of the inequality is less than the right hand side of inequality in the second case. Basically, I wanted to tell you, in the second case, the right hand side of inequality is less than the right hand side of inequality in the first case. So the answer will be second case. Second case, this is the required angle alpha, because because this alpha is less, so you will naturally prefer this angle, because after this value of alpha, if you increase more than the angle of the incline more than this value obtained in the second case, then it is not going to slip, but this is going to slip, and you want to avoid slipping of both, so you will naturally select the lesser value of tan alpha, and that's your answer. That's your answer. You can write it something like alpha is less than equal to tan inverse mu 3M1 upon M2 divide कर दो plus 4 divided by 2 M1 by M2 plus 1, and like this. This is your answer. Thank you very much for watching.